Hello everybody, my name is Geeta Krishnan. I am giving this presentation as part of my course Introduction to Photonics, and my course instructor was Dr. Shivananju Banan Nanjunda. So last time we were talking about the different topics in the photonics like ray optics, wave optics, electromagnetic optics, and the last part is the quantum optics. So as we have discussed, here the optics phenomena are explained based on different theories, and some of them were explainable with ray optics theory, and some of them were explainable with the wave optics, and some of them with electromagnetic optics theories. But there are some phenomena which cannot be explained based on these three concepts, but those are explainable if we consider the quantum nature of the light. So that part is considered as the quantum optics. So Max Planck and Albert Einstein were the scientists who started some experiments or some theories based on the quantum nature of the light. So Max Planck suggested that the light emission or absorption is quantized, and Albert Einstein suggested that the light itself comprises quanta of energy. So these two scientists have made a debate in this quantum optics theory. So there are certain optical phenomena like absorption, emission, spontaneous emission and stimulated emission which cannot be explained based on the electromagnetic theory of light. So their quantum nature of the light will come into help. So using the quantum nature of the light, we can explain about absorption and emission. So in the quantum perspective, the light consists of particles called photons. And the photon carries electromagnetic energy and momentum. So a photon has a zero rest mass and it travels at the speed of the light in vacuum. That is 3 into 10 raised to 8 meter per second. And Einstein's equation will give the energy associated with a single photon, which is given as hc by lambda, where h is the Planck's constant, c is the velocity of the light, lambda is the wavelength. So that can be reduced to 1.24 electron volt divided by lambda, where lambda is expressed in micrometer. So mainly in quantum theory, there are mainly three basic operations which will help us to explain almost all the optical phenomena which are happening. They are absorption, spontaneous emission and stimulated emission. So in absorption, there is a single photon which is coming with a particular energy. Usually that energy will be equal to the energy band gap of the material. So that energy will be absorbed by the electron which is there in the lower energy state. Here it is represented as E1. Those electrons will absorb this energy and will get excited to the higher energy level E2, and that is what is named as absorption. And in the case of spontaneous emission, there is no external force or external particles are involved. So here the electrons which are already there in the excited state will come to the ground state by emitting energy, and that energy is usually emitted in the form of light. And in the case of stimulated emission, there is a single photon which is responsible or which will stimulate the excited electron to come to the lower energy state by forcing it to emit the energy, and that energy will be emitted in the same, or that energy will be emitted with the same characteristics as that of the incident photon. So that is what is called a stimulated emission. So these are the explanation given for the each of these processes. So there, one of the main topic is the absorption spectroscopy. So absorption spectroscopy is a method that uses the wavelength dependent absorption characteristics of the materials to identify and to quantify the specific substances. So each of the substance will be associated with a particular characteristics. That means it will be absorbing a particular wavelength of light, and depending upon the output spectrum, which we will decide which wavelength is absorbed or which wavelength is transmitted, and based on that we will decide about the characteristics of the material. So that is what is done in the absorption spectroscopy. So here there is a measurement of the transmittance T or the absorbance A of the sample or solutions, and based on that we will characterize the material. So here it is given a simple example. P0 is the incident power of the light and P is the transmitted power of the light. So log of P0 by P will give the absorbance, and transmittance is given by the ratio of P by P0. So absorbance can be represented as minus of log of transmittance. So and that absorbance value is directly proportional to, or it is equal to, epsilon into BC, which is termed as the Beer's law. Here B is the path length, C is the concentration, and epsilon is the molar absorptivity. So the concentration of an absorbing analyte is linearly related to the absorbance, and it is represented by the Beer's law. So this will help us in characterizing the material. So depending upon the transmitted power and the incident power, we can know what is the wavelength which is absorbed, and depending upon that wavelength we can characterize the material. There is another type of absorption spectroscopy, that is UV visible IR absorption spectroscopy. So here they are using a device called diffraction gratings. So diffraction gratings, which will do a simple function that it will split the incident light into multiple beam paths through diffraction, causing the light of different wavelength to propagate in different directions. So based on the wavelength, it will differentiate the light. So each of the wavelength will be traveling in a different direction. That is what is done by the diffraction grating. So mainly there are single and double beam instrument for the absorption measurements. So in the single beam measurement, we are having a sample compartment in which we will put the reference cell, and we will take what is the absorbance value or what is the transmitted power and what is the incident power, and the same measurement we will do with the sample for which we want to characterize the material. So we will do one after another, and we will do the detection of the light, and we will calculate detect the power, and based on that we will do the characterization of the material. In the double beam instrument, we are having two paths, and in one path we will be putting the reference cell, and in the another part we will be putting the sample for which we need to characterize. So a single beam instrument records the ratio of the incident beam energy to the transmitted beam energy, similar to what we did here actually. So here what we did, we are having the incident power and transmitted power. Based on that thing, we will calculate the absorbance value. The logarithm of this ratio is the absorbance of the sample, and the ratio is obtained by taking the reading at the detector with no sample in the light path and subsequently with the sample in the light path. So the ratio of recording is achieved by using beam splitter and pulsed light source. So in absorbance spectroscopy, we are taking the ratio of the power, and based on that thing we are calculating the absorbance value, and based on that value we are characterizing the material. But in the case of double beam instrument, the incident beam is split into two portions, with one portion passing through the sample and the other portion passing through the blank reference solution. So ratio of these two powers will be recorded, and based on that thing the characterization of the material is done. And here it will show the UV visible spectrophotometer. So here we are having a deuterium lamp and a tungsten lamp. And there is a filter and there is a monochromator. So this will help us in deciding the wavelength, and that will be passed through a beam splitter. It will split the signal into two different parts. In one path we are having the reference solution, and in another path we are having the solution for which we need to do the characterization. And we are having two photodiodes, and then whatever power is received by the photodiodes will be converted into the electrical signal, and we will do the processing and we will do the computation of the absorbance value, and based on the wavelength which is absorbed or which is present in the spectrum, we will characterize the material. Another important topic in quantum optics is the fluorescence. So fluorescence is the phenomenon that a material emits light at one wavelength when it is illuminated by another wavelength. So we are having a light which is having a wavelength of lambda 1, and we are exciting the material with that wavelength, but it will be emitting another wavelength actually. So it will absorb light at lower wavelength, that is called the excitation, and it will emit light at the longer wavelength. So the lower wavelength will be having the higher energy and longer wavelength will be having the lower energy. So the basic working principle is explained by 4 steps here. So we are having the ground state and the excited states, and the photon is coming which is having a particular energy, and absorbing this energy the electron will be excited from the ground state to the excited state, and there is some transition called vibration relaxation. So in that, the excited state electrons will be just moving to some lower state, and from there it will be moving to the ground state by emitting energy which will be emitted as another wavelength, which is emitted as light in another wavelength actually. So here the absorption is done to a different energy state, and the emission is done from a different energy state. So the two different wavelengths are involved in this process. So that is the main principle of fluorescence. And it will represent the timing of fluorescence. Usually the fluorescence will be happening very fast, and there is another thing called phosphorescence which will be taking long time. So the light emission will be sustained for a long time in the case of phosphorescence compared to the fluorescence. So in the fluorescence spectroscopy, the light source is there and the optical filter will be giving the filtering of the signal or the light, and it will be passed through the fluorescent sample. So as part of that, it will be transmitting one wavelength and it will be generating another wavelength actually. So this 90-degree configuration will help in separating the excitation from the emission, and that emitted signal will be detected by a photodetector and do the processing. And the next topic is the optical sources. So for the first optical source which we will discuss is the laser. So the main principle in the laser is the absorption, spontaneous emission and stimulated emission. So as we discussed earlier, there is an energy photon which is coming. So from the photon it will be absorbing the energy and the electron will be excited to the higher energy state. And during the spontaneous emission, whoever is having the higher energy will be coming back to the ground state by emitting some energy which is emitted as light, and that is what is called the spontaneous emission. And in the case of stimulated emission, the photon will be exciting the photon will be stimulating the excited electron to come back to the ground state by emitting some energy, and that energy will be incoherent with the incident energy. So the photons which is emitted, which will be having the same characteristics as that of the incident photon. So the basic concepts in the laser is the population inversion. So the population inversion is a state of achieving more number of atoms in the excited state compared to the ground state. So in the normal state, we are having lot of atoms in the ground state. So by pumping, that means when we are giving the energy to the material, the electrons, from the ground state, the electrons will be absorbing that energy and will be get excited to the higher energy state. So the number of atoms in the excited state should be more compared to the ground state. So this is the one of the main condition which is a requirement for the lasing action to happen, and that process, that phenomenon is called the population inversion. That means we are inverting the population from compared to the ground state, because earlier the population was more in the ground state, but once the pumping or the energy supply is done, the in population will be more in the excited state. So that is the inversion of the population. So that is what is called the population inversion. That means we are having more number of atoms in the excited state compared to the ground state. And the pumping is the mechanism of exciting the atoms from the lower energy state to the higher energy state by supplying energy from the external source. So for the lasing action to happen, pumping is a mandatory process to be done. And this is done by using an energy, supplying energy from an external source. And the other one is the active medium. So a medium in which the population inversion is achieved for laser action is called the active medium. So this medium can be liquid, gas, plasma, etc. Optical resonators, a pair of concave mirrors placed on either side of the discharge tube, one completely polished and another partially polished. So this will provide the feedback for the generated photons. So similar to the electrical feedback, the optical feedback is given by the concave mirrors which are placed on either side of the discharge tube, and the light will be emitting from the partially polished mirror. So here it will show the basic part. Here there is the pumping process, and here those two are the concave mirrors. The active medium is shown here, and this cavity, which is the cavity, is nothing but the structure formed by the two concave mirrors. This cavity will help us in providing the feedback, and the output will be coming out from one of the mirror which is having the partial reflectivity. So the key elements in the laser are the pumping process prepares amplifying medium in suitable state. The optical power increases on each pass through the amplifying medium. If gain exceeds loss, device will oscillate, generating a coherent output. So there are some losses which is associated with the cavity, and the active medium will be having in the active medium, the population inversion will happen, and the optical feedback also will amplify the signal. So once the gain is overcoming the loss, then the lasing action will start happening, and all the photons which are generated will be having the same characteristics, so it will be providing a coherent output. Usually for the optical sources we are using the direct band gap material. Mainly there are direct and indirect band gap material. So the main difference is that if we consider the conduction band and valence band, so the lowest energy of the conduction band and the highest energy of the valence band will be having the same momentum in the case of direct band gap material as shown here, and it will be having a different momentum in the case of indirect band gap material. So usually the optical sources will be having the characteristics of direct band gap, because in the case of indirect band gap, the extra energy will be emitted as phonons, or the heat dissipation will be happening there. So in the case of laser, we told that pumping is a mandatory process to be done, and here there are two types of pumping, mainly 4-level pumping and 3-level pumping. So in the case of 4-level pumping, we are having 4 different energy states, which is represented as 0, ground state, 1, 2 and 3. So here when we do the pumping, the electrons or the particles from the ground state will be excited to the level 3, and the level, because the main thing which we need to do is a population inversion. So here the population inversion will be happening between the levels 2 and 1. So the number of particles or the atoms in the level 2 should be more compared to the number of atoms in the 1. So whatever atoms are coming to the level 2, they should be remain there for as much as time as possible. They should remain there for a long time. But that number should be high compared to the number of atoms in the level 1. So the whoever or whatever atoms are coming to the level 1 should be remain there for a very short time, and they should vacate that space as soon as possible. So that is why we are classifying the level as long-lived and short-lived. So the ground state is there, and the third level is the short-lived level, because the lacing action will be happening from 2 to 1. So whoever is coming at the third level should come to the second level as soon as possible, because we want to make the number of atoms or the electrons in this level 2 should be as high as possible, and the number of electrons in the or the number of particles in the level 1 should be as low as possible. So that is why we termed the level 3 as short-lived and the level 1 as short-lived and the level 2 as long-lived. So the electrons, after getting the energy from the pumping source, will get excited to level 3. They will decay rapidly to the level 2, and they will be remaining there for a long time compared to the other levels. And once the electron are going to the level 2 after emitting some energy, those energy will be emitted as light source, and the as soon as they reach the level 1, they should decay to the ground state. So there the decay is also a rapid process. So from level 3 to level 2 and from level 1 to level 0, the rapid decay should be occurring. Then only we can say that the number of atoms in the level 2 is high compared to number of atoms in the level 1, which is nothing but the population inversion. So here 4 different levels are there, and hence it is called the 4-level pumping. In the case of 3-level pumping, the lacing action will be happening between the intermediate state and the ground state itself. So here, as soon as the particles or the atoms reach the level 3, they should decay rapidly to the level 2, and from level 2 to level 1, they should uh, decay by emitting some energy, which is in the form of light. So here we are having 3 different levels, and hence it is called the 3-level pumping. So the one of the main application is the optical amplifiers. One of the example is the EDF, erbium doped fiber amplifier. So usually conventional silica fiber doped with erbium is used as the fiber amplifier. So here the erbium material, which is a rare earth element, is excited with or illuminated with a light energy at a suitable wavelength. Usually we will use 980 nanometer and 1480 nanometer for pumping, and it will be exciting the electrons to go to the higher energy state. So the 980 nanometer pumping will excite the electrons to higher energy state, where it will be living for a short time, and it will move back to a quasi-stable intermediate state. So usually from there it will go to the ground state by emitting energy at the range of 1525 to 1565 nanometer. Or if we are pumping by using 1480 nanometer, it will be directly jumping to the quasi-stable state, and from there it will decay to the ground state by emitting the 1525 to 1565 nanometer wavelength light. This is the basic working of an EDFI. So laser can be considered as an optical oscillator. So real lasers are not perfectly monochromatic, because several broadening mechanisms widen the frequency of the emitted photons. So if we are saying that it is monochromatic, only single wavelength or single frequency should be emitted, but in the real lasers that is not possible due to the line width usually, and hence it will be having a spread actually. So the exact wavelength or the line at which this occurs is determined by the characteristics of the laser medium, that is the active medium which we are using. And each laser wavelength is associated with a line width, which depends on the several factors like the gain, bandwidth of the lasing medium, and the design of the optical resonator. To sustain the gain as light travels back and forth between the mirrors, there are some conditions to be satisfied. The waves which are coming after reflecting from the mirror should remain in phase and reproduce their wave pattern, which means that the gravity round trip distance must be an exact multiple of the wavelength. So the cavity length into 2 should be equal to a multiple of the wavelength. Then only the photons which are traveling after reflecting will be in phase with each other, and if they are in phase with each other, then only they will be interfering constructively and producing a coherent light. So here lambda is the laser wavelength and n is an integer called the mode number. So the wavelengths that satisfy this resonance equation are called the longitudinal cavity modes. So there are different wavelengths which are generating inside the cavity, but there are certain wavelengths which are satisfying this equation which are constructively interfering. So that means there are some wavelengths which are destructively interfering, which will be getting destroyed. So only those wavelengths which are satisfying this equation are sustaining in the cavity, and those are called longitudinal cavity modes. So the actual output wavelengths of the laser will correspond to the cavity modes that fall within the gain bandwidth. So here this will show the gain bandwidth of the active medium, and here it will show the different wavelengths which are satisfying the condition that n lambda is equal to 12, and only those wavelengths which are having which are there in the range of this gain bandwidth will be sustaining inside the laser. So that is shown in the third picture. So even though there are lot of longitudinal modes getting generated inside the cavity, all of them will not be getting sustained inside the cavity. So only those wavelengths which are coming in the range of this gain will be sustained in the cavity, or that will be coming as the output of the laser. So the laser light is highly monochromatic, highly directive, and highly coherent. So usually materials are classified as insulator, semiconductor, and conductor based on the band gap separation between the conduction band and the valence band. In the case of insulator, it will be having large band gap. Usually it will be greater than 5 electron volt. In the case of semiconductor, it is less than 5 electron volts, 0 to 5, and in the case of conductor, it is overlapping. So we can say that the gap is almost equal to 0. So another light source is the LED. So LED is nothing but a PN junction. So it is like a PN junction here. We are having a P-type material, we are having an N-type material. So these two materials are joined to produce a device called a PN junction, and this junction will be connected with a battery in the forward biased mode, and then the junction, the recombination will happen between the electrons and the holes, and then they will be emitting the energy in the form of light. That is what is happening in the case of LED. So when no voltage is applied across the LED circuit, the electrons and the holes in the P and N region respectively remain stable. But once the voltage is applied to the LED, the circuit is forward biased. Hence the electrons present in the N region starts moving towards the holes present in the P region, and the electron-hole pair recombination takes place in the active region of the circuit. As holes are positively charged and the electrons are negatively charged, the light is emitted by the recombination of the holes and electrons. The release of the photon is due to the energy differences of the holes and electrons. So according to the energy band gap theory, the electrons present in the conduction band have higher energy than the holes in the valence band. So once the recombination is happened, this extra energy will be emitted in the form of photons, and that is coming as the light. So the LED is the PN junction which is forward biased to emit the light, and the energy is represented by h mu, where mu is the frequency of the light. And here it will show the basic connection. As we can see, the p type is connected to the positive and the n type is connected to the negative. So once it is forward biased, the electrons will be recombining at the depletion region and the extra energy will be emitted in the form of photons. So the semiconductor materials that are used for the construction of the LEDs have an energy difference between the holes and the electrons equal to visible light energy range. And when the electrons and the holes recombine in the active region, the energy of the electron releases in the form of a photon of visible range. And this phenomenon is called the electroluminescence. So always remember that electroluminescence is the phenomenon which is behind the working of the LED. The next topic is the photodetectors. So the photodetector is a device that measures the photon flux or the optical power by converting the energy of the absorbed photons into a measurable form. So the photodetector means it is a detector for the photons actually. So one photon will be coming with a particular energy and that energy will be converted to a measurable form. Usually it will be a voltage or a current. So usually there are mainly two categories, that is photoelectric detectors and the photothermal detectors. So in the case of photoelectric detectors, the absorption of the photons by a material causes the electron transition to a higher energy levels, resulting in mobile charge carriers. That means the photons which are coming will be converted to an electrical current, and that current or the voltage will be measured to quantify the photon which is incident on the photodetector. So under the effect of in the case of photoelectric detectors, the photon will be coming, they will be hitting on the detector. The detector will be converting that photons into a movement of charge, mobile charge carriers, and there will be a electric field. Under the influence of this electric field, these carriers will be moving and they will produce a measurable electric current. And from that current, we can quantify the amount of light which is incident on the material. So this photoelectric effect takes two forms, that is external and internal. And in the case of photothermal detectors, they will be converting the photon energy into heat. But it will be little bit slow compared to the photoelectric detectors, as there it will be taking some time to affect that or for a temperature change to happen, for a temperature change to be reflected in the case of so whenever there is a photon concentration change, that should be reflected as a temperature change, but it will take some time for this effect to happen. So it will be, this is a little bit slow compared to the photoelectric detectors. So the main photodetectors which in their photo detectors which are based on the photoelectric emission are usually photodiodes and phototubes. So one type of device is called the vacuum photodiodes or phototubes. So there we are having a photocathode which is connected to a negative voltage, and there is an anode which is connected to a positive or ground. And once the energy photons are incident on the cathode, it will be exciting the electron, and the electron will be get excited, and those electrons which are having the negative charge will be attracted by the anode which is having a positive charge compared to this electron. So this the electron will be moving from one material to the other material, and hence it is called the external photodetector. This will come under the category of external photodetector. And another method is the phototube actually. So here there is an inbuilt amplification which is happening. So similar to the photo diode, the photon will be incident on the photocathode. It will be exciting the electron to emit from the material, and that electron would be attracted by another electrode called diodes, which are kept at a positive charge relative to the photocathode. So the electrons will be getting attracted by all these diodes, and when the electrons is hitting on the diode, it will be excited, it will be stimulating another electron to get excited. So the number of electrons which are getting excited or which are getting liberated at each of the hit will be increasing. So at the end, when it reaches the anode, it will be having a large number of electrons compared to the number of electrons which are emitted from the photocathode. So this will provide an amplification, and it will be more sensitive compared to the photodiode or vacuum photodiode. So here there is an inbuilt amplification, but that is not happening in the case of photodiode. So this type of process or this type of device is called the photomultiplier tube, where an inbuilt multiplication is happening. Another term is photoconductivity. So in the case of photoconductivity, we are having a semiconductor material which will be connected with an electric field, and once the photon is incident on the semiconductor material, it will be generating the charge carriers which will be attracted by or which will be influenced by the electric field, which will be producing a moving charge carriers, and that current is measured to quantify the photons which is incident on the detector. So that is what is happening in the case of photoconductor. And in the case of photodiode, it is similar to what we discussed earlier. It is a light detector used to convert light into current or voltage based on the mode of operation of the device. So usually the photodiodes are classified as PN, but the basic working principle is the absorption. That means an incoming photon is coming, so that will be the electrons which are there in the ground state will be absorbing energy from the photon, and it will be getting excited to the higher energy state. So electron hole pairs are generated, and these electron hole pairs will be moving under the influence of an electric field, and that will produce a current or voltage, and that can be used to measure the used to quantify the photon which is incident on the material. So the main categories are PN photodiode and PIN photodiode and avalanche photodiode. So the photo detection mainly happens in the case of depletion region of the diode. But in the case of PN photodiode, the diode is very small and the depletion region is also very small, and hence whatever light is incident on the material will not be getting converted to the electron hole pairs because the electron hole pair generation will happen only in the depletion region. So since the depletion region width is very small, only a part of the light which is incident on the material will be getting converted to the electron hole pairs, and hence so in the case of PIN photodiode, this issue of the smaller depletion region width is solved here. So here in between two PN junctions, we are sandwiching an intrinsic layer which will be wider in area. So most of the light which is incidenting on the depletion on the region between the P and N junction will be getting converted to the electron and hole pairs. So the quantification will be more accurate. And in the case of avalanche photodiode, the structure is we are having highly doped P side and N side on either side, and in between that there is a P type material and an intrinsic material here. So here there is a process called impact ionization which is happening. That means when the when the photon is incident on the material, it will generate electrons and hole pairs, and that will be getting accelerated in the presence of an electric field, and that will be giving an amplification for the output signal. So more electron hole pairs are generated due to impact ionization. An additional factor is introduced to impact ionization, which increases the photocurrent several times, and that is called the avalanche multiplication factor. It is like PN diode or PIN photodiode, where the electron hole pairs are generated due to absorption of photons. But so here the electron hole pairs are generated due to absorption of photons. But in addition to this, the avalanche photodiode uses the impact ionization principle for increasing the magnitude of the photocurrent. So here the electric field which is present will accelerate the electron hole pairs and creating and helping them to generate more number of electron and hole pairs, and that will increase the magnitude of the photocurrent which is obtained at the output. So the figure of merit of the photodetector are the sensitivity, that is the maximum output photocurrent at the given input photons or optical power, and the efficiency is the it will be a quantification of the conversion from the photons to electrons, and the response time is the how much fast it can respond to a change in the input. So the fast response to operate at high frequency, and for a photodetector the signal to noise ratio should be as high as possible, and the another figure of merit are the high reliability and the low cost. One of the main parameter of a photodetector is the quantum efficiency. The quantum efficiency is represented as the ratio of the electron hole pairs generated and collected to the number of incident photons, that is current divided by electron charge of the electron divided by power divided by energy of one photon, that is hv. And the responsivity of a photodetector relates the electric current IP flowing in the device circuit to the optical power P incident on it. So the responsivity is eta E by h mu, where eta is the quantum efficiency, E is the charge of the electron, H is the Planck's constant, and mu is the frequency. So in the modern era, the most of the cameras are digital cameras, and they will be having the solid state electronic sensors on it. So there are millions of discrete photodetector sites called pixels in the optical sensor, and these sensors in machine vision fall into one of the two categories, that is the charge coupled device and complementary metal oxide semiconductor imagers. So the sensors or the photodetector cells which will be falling into either of these categories. Now next comes the optical modulators. So in the optical modulators, we are modulating one of the parameter of the light wave. It can be amplitude, phase, polarization, wavelength, time, or precision. So the categories are optical modulators mainly classified into absorptive and refractive. The refractive is again classified as electro-optic and acousto-optic. Electro-optic is divided into phase, amplitude, and polarization modulation. So in the case of acousto-optic modulator, the refractive index of the optical medium is altered by the presence of the sound. So the sound wave will be creating a perturbation and perturbation of the refractive index, and that will look like the form of a wave as shown in the figure. So there will be compressions and the rarefactions, and This refractive index variation is caused by the sound variation. So here the pattern is having a period of capital lambda. So the light, when it passes through this perturbed time varying homogeneous medium, it will be getting modulated actually. So that means it will be similar to the diffraction grating. So the different wavelengths will be directed to different directions. So, and the refractive index variation will be caused by the sound waves. The sound wave variation will be there. So that variations will be causing a variation to the refractive index. So this refractive index variation will be responsible for making the different wavelengths in the light to direct into different directions, and that is how the acousto-optic modulator is working. So in the case of electro-optic modulator, the electro-optic modulator is a device which can be used for controlling the power, phase or polarization of a laser beam with an electrical control signal. So here the controlling signal is electrical signal. In the previous case, it was an acoustic signal. So here, using this electrical signal, we are varying the refractive index. In the earlier case, the refractive index variation is happened due to the acoustics or the sound variations. So the Frederick Pockels and John Kerr were the pioneers in the electro-optic modulator area. So the electro-optic effect is a change in the refractive index that results from the application of a steady or low frequency electric field. So when the electric field is applied, the refractive index varies, and since the material's refractive index is varying, that will affect the light which is passing through it. So when we control the electric field, it will control automatically the light also. So the main important concept here is Pockel's effect and Kerr effect. So the refractive index changes in proportional to applied electric field. Then that effect is called the Pockel's effect. It is a linear effect. And Kerr effect is a non-linear variation of the refractive index with respect to the applied electric field. So it will be varying as square of the applied electric field. And the next modulator type is electro-absorption modulator. So here the change of the absorption characteristics of a medium in response to an applied electric field. So when we apply the electric field, the absorption characteristics of the material will change. For example, here we are having a band gap and which is when a photon of energy h mu is incident on it. Eg is the energy band gap. The electron hole pair will be generated here. So when there is no electric field applied, it will be looking parallel. When the electric field is applied, there will be a variation in the orientation of the conduction band and valence band. So hence there is a change in the energy band gap. So the light which is coming from outside will be getting absorbed or will be getting transmitted depend upon the corresponding energy band gap which is created. So if the energy band gap is equivalent to the photon energy, it will be getting absorbed. So the output we will be having less power. But if the energy band gap is not matching with the energy of the incident photon, it will not be getting absorbed, it will be getting transmitted. So the output power will be more. So that is how the modulation of the light is happening here. So the next topic is the nonlinear optics. So the optics is mainly classified as linear and nonlinear. So linear optics is termed as the optics of weak light, and the superposition principle is valid here. In the case of nonlinear optics, the light intensity is much more compared to the linear optics case. Here the superposition principle is not valid. So here there is an input wave. In the case of linear optics, the input wave and the emitted wave will be having the same color. That means they will be having the same frequency. But in the case of non-linear optics, the input wave will be having a different color compared to the emitted wave. So that means new frequencies will be getting generated here. So usually the optical linearity is happening because the applied electric field distorts the cloud and displaces the electron. So it can be compared with the mass on a string. So we can consider it as a dipole which is having polarity of positive and negative on either side. So the dipole moment per unit volume is called the polarization. So the separation of the charges will give rise to a dipole moment, and the dipole moment per unit volume is called the polarization. The separation of charges is because of the applied electric field. So this will cause the nonlinearity of the material. So when electromagnetic waves propagate in a material, the atoms and molecules oscillate at frequencies of the electric field associated with that waves. The field associated with the EM waves polarizes the molecules in the medium, displacing from their equilibrium positions and induces a dipole moment which is given by P is equal to QD. So the polarization P, that is the dipole moment per unit volume resulting from this induced dipole, is given by P is equal to N into Q into D. And the polarization effect of the field on the molecule dipoles depends both on the properties of the medium and on the field strength. That means P is equal to epsilon 0 into I into E. So the applied electric field will affect the polarization. So the branch of physics which deals about the interaction of high intensity laser light with matter, in which the polarization density P responds non-linearly to the electric field E of the light, is called nonlinear optics. So the polarization P is a non-linear function of the applied electric field. That is what is happening in the case of non-linear optics. But in the case of linear optics, the polarization is just a linear function of the applied electric field. So there is an example given as potassium dihydrogen phosphate. So here it will be converting the invisible light lambda, that is 1064 nanometer, into a visible green light of 530 nanometer. That means frequency doubling is happening here. So the light will be interacting with a non-linear material here and creating new frequencies. So here it is showing some basic difference between the third order nonlinear optical effects and second order nonlinear optical effects. So in the case of linear medium, the polarization is a linear function of electric field. But in the case of nonlinear medium, the polarization is a non-linear function of the applied electric field. So depending upon that, it is classified as second harmonic and third harmonic generation. So in the case of second harmonic generation, a non-linear optical process in which two photons of high intensity light interacting with a non-linear material are combined to form a new photon with the twice the energy and therefore the twice the frequency and half the wavelength of the initial photons. That means we are having two frequencies, omega 1, omega 2, both of them are equal. And in that case, these two photons are interacting with a non-linear material, and as a result it will be producing a new frequency which is twice the frequency of the incident photon. That is what is called the second harmonic generation. So in the second harmonic generation, we are incidenting the signal with a particular frequency. So two photons with the same frequency will interact with the non-linear material and it will be producing a frequency which is twice the frequency. That is what is called second harmonic generation. And the third harmonic generation, it will be producing a frequency which is third time the original frequency. So that is what is called third harmonic generation. So here the first one is a linear optic part, that is omega 1 is the frequency of the incident photon and omega 1 is the frequency of the emitting photon. So both of them are having the same frequency. But in the case of nonlinear optics with second harmonic generation, that means it will be represented by the term P is equal to chi raised to 2 into E square. That means the electric field is a the polarization is a nonlinear function of the electric field. That is, this is the quadratic function. So in that case, omega 1 and omega 2 are omega 2 photons with same frequency are interacting and it will be producing another frequency which is omega 2. And in the case of third harmonic generation, 3 photons of same frequency will be interacting and producing a new frequency which is 3 times the original frequency. That is what is called third harmonic generation. And the term which is responsible for third harmonic generation is x raised to chi raised to 3 into e raised to 3. And chi raised to 2 into e raised to 2 is the one which is responsible for the second harmonic generation. Next topic is the frequency mixing. So in the case of optical second harmonic generation, there is an example given as ruby laser. So there is a potassium dihydrogen phosphate crystal. So if we are incidentally that material, which is a non-linear material with a 694 nanometer, which is red light, it will be producing a new frequency called 347 nanometer, which is in the UV range. And in the case of neodymium YAG laser also, it will be producing twice frequency doubling, and the same thing will happen in the case of aluminum gallium arsenide laser also. So all these can be termed as, or all these are examples of second harmonic generation. The next type is the sum frequency generation. So here two different frequencies omega 1 and omega 2 are interacting with a nonlinear material and it will be producing a new frequency which is sum of the two frequencies. And another thing is different frequency generation or different frequency mixing. So here also two different frequencies omega 1 and omega 2 are interacting with a nonlinear material but creating a new frequency which is just the difference between the two frequencies. Earlier it was the sum, here it is the difference. And in the case of four-wave mixing, so three optical fields will be mixing in a nonlinear medium and it will be creating a fourth wave. That is what is happening in the case of four-wave mixing. The next topic is the scattering. So mainly there are three types of scattering: Rayleigh scattering, Raman scattering, and Brillouin scattering. So in the case of Rayleigh scattering, no energy transfer occurs and the scattered light retains the same frequency as that of the incident light. So as we can see from the figure, mu1 is the frequency of the incident photon and the same frequency is there for the emitted photon also. So it can be considered as a linear elastic scattering. So it is caused by the presence of submicroscopic variations in the density and composition of the material. The next type is the Raman scattering. So the material will give out or absorb energy to the incident wave. So if we are incidenting the nonlinear material with a frequency mu1, it will be creating another photon which will be having a different frequency which can be either higher than the incident photon or lower than the incident photon. So based on that, we are having two different categories of Raman scattering, that is strokes and anti-strokes. If the emitted wave has less energy compared to incident wave, it is called a strokes Raman scattering. And if the emitter wave has more energy compared to the incident wave, it is called the anti-strokes Raman scattering. The main reason for the Raman scattering is the light interaction with the molecular vibrations or the rotations. And the frequency shift in the case of Raman scattering is of the order of 10 terahertz. In the case of Brillouin scattering, the interaction of light wave with the lattice vibrations of the medium is the reason. So that means the light is interacting with the lattice vibrations of the medium and it will cause the Brillouin scattering, and here the frequency shift is in the order of 10 gigahertz. So these are the main things which we need to know about the quantum optics and the nonlinear optics. Thank you very much.